Hello, my name is Pablo Vaquero, and today I will be talking about the project on non-traditional machining. Okay, so in this project we are required to design different non-traditional machining processes for three different applications. The first one is regarding defense, the second one is regarding medical services, and the last one is about sustainable energy. Okay, so regarding the project in defense, we were required to design a 10-inch octagonal slab for an for an heliport, and the main requirement was that the cast must have parallel walls. So in order to do so, I think that the best option would be wire electrical discharge machining. Okay, the main reason is because the material was the material that we are given is very hard and difficult to machine metal alloy. And this method is good for hard materials. Then it is also important to have a really good precision as the octagonal shape is required. Uh, Together with the parallel walls. So this method is also really good in high precision machining. Then also the avoiding direct contact is going to be main characteristics of the non-traditional machining methods that will be discussed in this presentation. And it's the same for every project. And basically this is good for materials where traditional machining would be really harmful. Um, in this way, we are minimizing the wear and stress suffered by the material. Um, and also another important feature is that the excess material or the dust is removed thanks to the use of the electrodes and the water jet that we're going to apply to the moving wire. And finally, the main critical step for this project is the precise movement required by the moving wire. The fact that we are told that parallel walls are required means that the precision needs to be really high, and so the angle of attack of the moving wire must remain constant at all times, and it's an important feature to take into account. Okay, so now I'm going to explain how this method works. So firstly, we need to understand that the main function of this method is thanks to sparks between the two electrodes. So basically the wire acts as a cathode while the workpiece is the anode, and they are separated by a fluid which is drawn here in blue, which is the dielectric fluid. And these sparks between the two electrodes generate heat that will melt and vaporize the workpiece material. And as you can see here, we have the dielectric fluid is pumped and passes through a filter and then is ejected into the part that we are cutting at that moment. Here we can see a zoom of what this wire does. The black dot here is the cross section of the wire that is cutting the material, and the small gap between the material and the wire is the spark gap. And basically the main process or the main steps include the first thing, preparing the workpiece. Then we need to select the electrode required, that is the material of the wire, which will depend on also the workpiece in order to have a good electrical transmission between both. And then we need to adjust the different parameters of the wire, such as uh, its speed and also the voltage that will be applied. Then we submerge the material into the electric fluid, initiate the first spark, and then the critical step, which is controlling the movement of the wire. As you can see here in the right, there's a picture of how the desired cross section of the or the top view of the slab would be in the end. And the most important thing, as I mentioned, is to control the angle of attack of the wire, which I named alpha, and alpha needs to be the same in the four cuts that will perform the machine. Now for the second project, pharmaceutical has contacted us in order to provide some medical services, and we are required to perform a very thin hypodermic needle that is specified to be sharp and bar-free. So in order to do this, I decided to use a combination of two methods, which are electrochemical grinding, or ECG, and electrochemical deboring, or ECD. Okay, I will call them like this in the next part of the presentation. So I selected these two methods because firstly they are good for conductive materials, which is the case of the medically used stainless steel. Then, as we need the needle to be very thin and obviously sharp, we require a high precision, and also the fact that it's sharp and bore free can be achieved using this method, as I will explain in the next slide. Also, electrochemical grinding is great in order to have an improved surface finish, which of course it's important for a needle. And I decided to use a combination of two processes, basically because I will start with a raw material, which will be a tubular shape stainless steel. Then I will perform ECG in order to create the needle. However, this would include some bars because they are very difficult to eliminate only with electrochemical grinding. And finally, I will perform ECD in order to perform a needle with no bars. The critical step, I think, is clearly detecting those burrs which can be difficult, and then removing them using ECD. Okay, so the first process to perform is ECG. So basically, ECG combines both the anodic dissolution and abrasive action. Basically, well, the abrasive action is quite straightforward. You just have a grinding wheel, which is going to perform some pressure in this part of the tube, and will start abrasing it. However, the anodic dissolution implies chemistry issues. Basically, we have that the workpiece will as the anode, while the grinding wheel would be the cathode, and the electrolytic flow would be the medium between both of them. So basically, the material from the anode would tend to go to the cathode, and the electrolytic flow will act as the main current from one to another. Also, it's important to note that there's a constant flow. The depleted material from the workpiece can easily and quickly be removed from the workpiece. This is, as I mentioned, an electromechanical process. The expected result can be seen here after rotating at a certain revolutions per minute, we can obtain the needle-shaped stainless steel tube. However, as can be seen in the picture in the right, this workpiece, this, even though it's in another color, this is the same as this. The drawing is not perfect, but here we can observe some bars that may have occurred during the action of the electrolytic flow and the grinding wheel. That's why we use ECD, in which basically we have here the cathode, the anode is the workpiece again, and now there's only anodic action, anodic dissolution. We have no more abrasive distortion. So we can see here how there's an insulation material which will avoid the conduction of material, but here in this yellow zone that I marked, the material from the workpiece would be attracted to the cathode, and that will be able to remove the burrs in the needle without clearly affecting or distorting the desired geometry of the needle. Okay, so in the last project, a sustainable energy company has contacted us because they need some glass covers for their solar panels. They require these covers to be rectangular and to have some holes in order to screw them. Also, these holes have to be perfect and there cannot be any cracks. So the method I used or I selected for this project was ultrasonic machining. This method is really efficient for delicate and brittle materials, such as the case of glass. Then this method can easily achieve complex geometries, and so holes would be an easy shape to perform. And then the ultrasonic vibrations are great in order to avoid the formation of cracks in the glass. So this would meet the requirement of not having any cracks in the glass. The critical step in this method would be selecting the right frequency of vibration for the machine, because if instead of ultrasonic they are just normal vibrations, then the the glass would immediately break. Okay, so the way of functioning is quite easy and straightforward. Basically, you have an oscillator and a piezoelectric transducer which will transmit the energy into vibrations. These vibrations are between 19 and 25 kilohertz and will be transmitted through the horn up to the abrasive slurry and the flow, which can be indicated in blue. This abrasive slurry contains some particles which are abrasive particles, which will also vibrate with the oscillations. So the repetitive movement up and down of the tool, together with the constant abrasion of the abrasive particles, will cause the material to start eroding by both chipping and grinding. And we can finally see how the workpiece will end up with the 4 holes done right here, and with no cracks, thanks to the high velocity of the high frequency of the vibrations of this method. So thank you very much for your attention, and I hope you enjoyed.